And let me give a short introduction and we can get started. Hi everyone, welcome to the last session of the spring seminar. So today we are happy to have Professor Simon Du here to give us a talk on his recent work. So Professor Simon Du is now an assistant professor in computer science and engineering in UW, and his research interest broadly in machine learning and deep learning and representation learning and reinforcement learning. And prior this faculty position, he was a postdoc at IAS at Princeton, and he completed his PhD in machine learning at CMU. And Simon's research has been recognized by Sloan Research Fellowship and Samsung AI Researcher of the Year Award, and Intel Rising Star Faculty Award and NSF Career. And without being verbose, let's get started. Thanks, Simon.
Right. Thank you for hosting me, and it's great to see this online seminar has been widely spread out around the world. I started like 4 years ago, and it's great to see how it evolves. So today I'm happy to talk about my research on optimization and some interesting phenomena on over-parameterization. Especially on how over-parameterization slows down gradient descent. Okay, so I think for the audience in this seminar, over-parameterization may be a familiar word. Where basically for this talk, over-parameterization just means the number of parameters in your model is larger than necessary. And I'll be more specific later about specific setting. And we've seen a lot of works actually on over-parameterization, mainly talking about its benefits. For example, for optimization, there's a line of work on landscape analysis showing it might help to eliminate a spurious local minimum. So simple algorithm can find the global minimum. And there's a line of work on neural tangent kernel, which I contributed to as well, where in that regime, you can kind of linearize the training dynamics of neural network and in the over-parameterized regime. And in that case, you can show global convergence of gradient descent for finding a global minimum. And also related to mean field dynamics, which also analyze the global convergence of gradient descent. So in optimization, generally speaking, there's a lot of works, maybe hundreds of papers showing over-parameterization is beneficial. And similarly, in generalization, people have found that even though you over-parameterize, you have more parameters, it does not really hurt the generalization behavior of the neural network. There's a line of work on double descent, which shows as model size increase, the test error can even decrease. And like there's a line of work on benign overfitting, which shows that even if the model with all data, it can still generalize well. So there's a lot of work showing over-parameterization is actually good for both optimization and generalization. So in this talk, I'll talk about some examples on whether over-parameterization is really beneficial or not. And I'll show you that in these examples, it's actually not for optimization. It's not about global convergence, but more about the convergence rate if you over-parameterize the model. Okay, so the first example I'll show you is on learning a single neuron. This is a joint work with my student Wei-Hang Xu. So this is a very classical model. It's called teacher-student setting, where we assume basically the Y, the target, is generated from some ground truth neural network, and we use neural network to learn it as well, and they're of the same architecture. So basically, we try to learn a two-layer ground truth teacher network G with, say, ReLU activation and, say, M neurons. So we denote them as V1 to Vm as the input is in RD. And this is ground truth formula. So basically, we assume second layer are all ones. And what our model is a over-parameterized student network, which we denote as F, which has n neurons. So here we consider over-parameterized network, which means that n is larger than m. Okay, so it's m neurons is necessary, and if n is larger than m, it is over-parameterized model. And our learning parameters are w1 to wn. Okay, so you can see here at least our neural network can represent the ground truth if n is as large as m. Okay, and again here, this notation just means ReLU activation function. The input dimension is d. Okay, so for this talk, I'll just focus on optimization. Okay, so there's no samples at all. Here, basically, we'll consider a population level loss function, and we even consider a simple case like this input x is sampled from a Gaussian distribution. So we consider this population loss. Just to simplify the problem a bit, because you can focus on optimization instead of statistical error in the analysis. So we focus on population loss, quadratic loss, and fx is our model, gx is target, consider this quadratic loss, and input is Gaussian. Okay. And for training, we fix the algorithm. Our algorithm just randomly initialize gradient descent. So our student network is just initialized with random Gaussian initialization. So for each neuron, we sample it from each entry sample from some Gaussian with some tuning, some variance sigma squared. Okay, and then we just run gradient descent with some learning rate eta. Okay, eta is a step size. Okay, so yeah, please stop me if you have any questions. I'm happy to have more interactions. Okay, so this is a very fundamental problem. You can see here, it's learning a ground truth neural network. It's quite natural and has been studied around 35 years ago by Yan LeCun. And there's an interesting phenomenon, which actually is about the benefit of over-parameterization. In experiments, people have found that if you do exact parameterization, which means that n equals to m, the same number for student and teacher neurons, then it's very hard for gradient descent to find a global minimum. You will often stuck at some local, suboptimal local minimum like here. The global minimum should be 0 because student network can exactly represent the teacher network. And but they found that if n is larger than m, like say some order-wise difference, say 10m, then you can just run gradient descent and find the global minimum of this non-convex loss function. Okay, so people have found this very interesting empirical phenomenon, and there's a long line of work trying to study this problem. But unfortunately, there's no theoretical really prove this phenomenon. Okay, and even for the case m equals 1. Okay, so even if there's only a single neuron, there's no global convergence analysis for the over-parameterized case when n is bigger than m. Okay, there's some prior work, like Gu et al. In 2017 showed that if you change the loss to some other loss, which enables some benign landscape, and then you can show global convergence of gradient descent. But the loss is quite unnatural, but in practice we just use square loss. And Li et al. Showed that in 2020, then showed that gradient descent can learn this two-layer network and it's better than kernel method. Okay, so which means that it can learn something that has better generalization error than neural tangent kernel method. But they didn't show a global convergence that show like you can achieve some threshold there. And Zhou et al. In 2021, they proved that a local convergence for any n bigger than m, but it's only a local convergence. And they also need to modify the network architecture, which is not natural as well. Okay. So here, our contribution for this line of work is that we consider one special case where we consider m equals 1. Just correspond to learning a single neuron, but you over-parameterize it, like n is still bigger than m. And we can show a global convergence for n bigger than m, for any n bigger than m. So you can kind of see our work as important first step for understanding for the general M case, which is still a widely open problem. Okay, so just another note that this problem cannot, this phenomenon cannot be explained by existing work like a neural tangent kernel, landscape analysis, because there are local minimum, and the neural tangent kernel requires a number of parameters, even larger number of data. But here we kind of consider population loss, which has infinite data, and it cannot be explained by the mean field dynamics as well. So it's a new regime, and no prior work has prove this phenomena even for m equals to 1, and we proved the m equals to 1 case. Okay, so that is about the convergence. What we found is more interesting is a convergence rate. So let's consider a case where we are trying to learn a single neuron, so m equals to 1. Okay, so these are the convergence rate plot for a different number of student neurons. So if you have also one neuron, and if in this case you converge to global minimum, so you have this red plot. So it's a quite nice plot. You can see here it's a global convergence. Sorry, it is converged to a very small loss, and it has a linear convergence rate. You see here it's a quite clear linear convergence. However, as long as you are in the over-parameterized regime where n is bigger than m, so in this case, n is 2 or 5 or 10, so you can see here the convergence becomes much smaller. So this y-axis is on the log scale, okay? So this is actually a sublinear convergence as long as in the over-parameterized regime. Okay, so this corresponds to these three plots, these three lines. And on the right is showing the log of the loss with number of iterations. So this is kind of, we try to find what is exactly the convergence rate. You can see here after taking a log is approaching -3. Okay. So basically, this empirical the simulation study shows the convergence rate of the loss is linear if you're in the exact parameterization case. However, it becomes sub-exponential, and this is exponentially slower when n is bigger than 1, when you are in the over-parameterized case. And this taking the log, which corresponds to a polynomial dependency on the loss, approaches -3, and this is from empirical observation, this is a much slower rate. Okay. So basically from the empirical simulation, we found that if in your over-parameterized, then the convergence rate is 1 over t cubed, okay, t to the -3. So basically, our main contribution for this is that we actually prove this is exactly the rate. Okay, so for randomly initialized gradient methods, we show that for both upper and lower bound, we give this t 1 over t cube rate. So the main conceptual finding is that this gives you a separation between exact parameterization and over-parameterization. Okay, so a lot of people have said like over-parameterization benefits optimization. Well, it can help you find the global minimum, but but in terms of convergence rate, actually over-parameterization can exponentially slow down the convergence rate, at least for this example. And we can actually prove it rigorously. Okay, so here let me give you a overview of the precise result. Basically, we show that if you do small initialization, the initialization scaling sigma is polynomially small in terms of the magnitude of the ground truth neuron, which we denote as V here. And you have small enough learning rate. It's kind of approaching the gradient flow regime, but you are in a small initialization, which actually corresponds to the representation learning regime instead of the or feature learning regime instead of the neural tangent kernel regime. So in this regime, we can show that its probability at least 1 minus delta gradient descent find the global minimum with this rate. So there's some polynomial dependency on the number of neurons, step size, and magnitude of the neuron. The rate in terms of number of iterations is 1 over t cubed. So in terms of analysis, it's again not a standard analysis because we need some specific analysis for this problem. So basically, we divide the convergence into several phases. The key quantity here is the angle between each student neuron and the teacher neuron, so which denote as theta I, which denote this angle between the ith neuron, ith learning vector Wi, and the ground truth vector V. In the phase 1, we can show that theta I decreases to a small value, so the angle kind of direction of neuron align with teacher neuron in the rapid phase. And then in the second phase, we can show that the magnitude of the student neuron align well with the teacher neuron. So the sum of Wj minus V, which measures the total magnitude of the student neuron, it matches the teacher neuron. And in the phase 2, the angle remains bounded. And then in the end, we enter phase 3, which is a local regime. We show that its convergence rate is 1 over t cubed. So how do we actually show the 1 over t cubed? There are several difficulties. I'll just briefly mention here. So first of all, remember we are using a ReLU activation function, which is not a smooth function, right? Specifically, even for this loss function, the Hessian is of the form like proportional to the norm of the underlying ground truth neuron V divided by the student neuron Wi. Okay, so basically, if you have even one neuron that is very, very small norm, then the Hessian will be very large. As the neuron goes to 0, the Hessian or the spectral norm of Hessian will go to infinity. So to handle this non-smoothness, Zhou et al. In 2021, they kind of artificially modify the neural architecture in this form so that this guarantees that the landscape is smooth. So you will not overshoot by using a very large learning rate. Okay. But our analysis, we show that you don't need to do this artificial modification because there are actually some, we can call it implicit bias of this gradient descent algorithm to guarantee that Wi, which is the norm of Wi, norm of neurons, is always lower bounded. Okay, so we'll not actually enter in a regime where, or in a region where it is non-smooth. So you always stay in the smooth region, but this requires analysis of the dynamics of gradient descent. Okay, so this is one difficulty. And how do we actually show this 1 over t cubed convergence? So again, we are inspired by this work by Zhou et al. They show that basically use this gradient lower bound idea to give a convergence rate in their local analysis. So they show that they consider the gradient, inner parameter gradient of the ith neuron, and the difference between ith neuron and the corresponding ground truth or corresponding global minimum, and show that this inner product is lower bounded by the loss function. Okay, and here remember we are in the over-parameterized regime, so actually we have infinitely many neurons or infinitely many global minimum. So in their case, in their papers, just pick any of them, and they can establish this kind of the inner product is proportional linearly to the loss function. However, if you just use this bound, you can now obtain this 1 over t cubed convergence rate. So what we did is that instead of arbitrarily pick a global minimum, we choose a specific global minimum in this equation. Okay, so if you choose a well-chosen global minimum, which is of this form, so the details are basically you consider specific direction on the student on the teacher neuron, and you project that your neuron on that direction, you consider norm on that. Then you can actually consider one specific global minimum, and you can use this to show that the inner product, okay, between gradient norm and the difference between your student neuron and this specific global minimum, it can lower bounded by loss to the 2/3. Okay, so the gradient norm lower bound now becomes loss to 2/3 instead of the linear in the loss. Okay, and the loss to the 2/3 gradient lower bound will give you 1/t³ convergence rate. So I'm not going into detail, but this is a high level idea. If you choose a specific global minimum in the over-parameterized case, in establishing this gradient lower bound, you can actually obtain a sharper rate, and it's actually tight. Okay, so this is one technical insights here. Okay, so now let's consider lower bound. Why 1/t³ is actually necessary. So first of all, you can observe that this is not always the case. So remember, our bound basically is about if you do random initialized gradient descent, you can find the rate is 1/t³. But actually, there are some specific initialization. If you start from there, then you will have a linear convergence rate, like exponential to the -t. So one toy case is that all student neurons are parallel with the student neuron, which is a toy case 1. So here I have V here, and all student neurons, they are aligned on the same direction as V. Okay. In this case, it's pretty much like a scalar problem. It's a converged linearly. But of course, if you randomly initialize case, there's 0 probability you will have all the student neurons on the same direction as the teacher neuron. And toy case 2 is that if all student neurons are equal, then this basically go back to the one student neuron case, and they also have linear convergence. So it's not very trivial that to prove this lower bound, so 1/t³, because it's 1/t³ only if you utilize some property of the random transition, so that you can distinguish from these two toy cases. So what properties we use? Basically, we require at high level, we require some non-degeneracy property. So specifically, we define this Di, which is a projection of Wi onto a orthogonal complement of the teacher neuron direction. Okay, and the non-degeneracy just means that Di's are non-zero, and dr they are not parallel. So every angle between Zi and Zj they are bigger than 0. But at the high level, this just means if you random initialize, it's naturally satisfied, because if you are degenerate, it has measure 0. Okay, so basically, Gaussian initialization symmetry breaking is almost surely non-degenerate. And with this two bond, with this condition, we can show that we consider this potential function, which measures the difference or the pairwise difference between Z and ZJs. And then we can derive a lower bound for dynamics of this potential function and relate that to the loss. So you can establish this 1/t³ lower bound of this form. Okay, so that's a high level idea. Basically, we need to utilize this non-degenerate property, and then you can construct a potential function based on the pairwise difference in the student neuron, and use that to establish a lower bound for the loss. So one key takeaway of this lower bound is that if you only have one student neuron, so in the exact parameterization case, then you cannot really construct the potential function, because you at least need to have two neurons, say I equals 1, j equals 2, to construct this potential function. But if you only have one neuron, n equals 1, you cannot even construct this potential function. So really, this the lower bound proof technique utilizes the we are in the over-parameterized case. Okay. All right. So that's basically the first part of my talk. Is there any question?
Just a very small question that
Yeah.
several slides ago you mentioned that you can lower bound the ratio between the teacher's neuron and the student neuron. So is this in this work or no?
Oh, do you mean the non-smoothness?
Yeah.
Yeah. This is in this work. So
Okay.
So yeah, so if this bound, right? So if this, let's say the teacher neuron, let's say this V is a constant, okay, because it's a ground truth. But if your student neurons norm is approaching 0, then it's non-smooth. So in our work, we basically show that it always has a lower bound as long as you run gradient descent. So basically, gradient descent automatically avoid this non-smooth region.
Okay, thanks.
Yeah, so this requires some dynamics, the analysis of the gradient descent dynamics. Yeah, you can check out our paper.
Okay. So
yeah, go ahead.
So basically, in general, in the first part, you are leveraging both the structures of initialization and the special global minimum, right?
Yeah, so for initialization, we just use random initialization, but we do need like small random initialization.
Mm-hmm. Okay.
And
those two conditions.
Yeah. So and then to this global minimum is a proof technique where we choose a specific global minimum to establish this sharper gradient lower bound, which can be used to prove the Swan or T cube convergence rate.
Okay.
Any other questions? Okay, so yeah, let's move on to the second example, which also has this similar behavior. This is joint work with Noya Xiong from Tsinghua and Li Jundeng from University of Wisconsin. Okay, so this is a classical problem. It's called matrix sensing. It's a very popular model. I would say before the age of deep learning, but still now serves as a kind of exemplar model to examine several important properties of deep learning theory. So the goal of matrix sensing is basically to recover an unknown lower rank matrix from some linear measurements. It has a lot of applications: image processing, signal processing, computer etc. And recently, people view this matrix sensing as a kind of exemplar model to examine different properties of deep learning. So it's a kind of a test bed. So it is non-convex. It has certain implicit regularization effect, incremental learning, like implicit bias and feature learning, etc. So let's first talk about symmetric matrix sensing. So here you have a low rank matrix M star. Let's say it's n by n. Let's say rank R, so R is smaller than n. So in matrix sensing problem, what you observe is this kind of the inner product between a sensing matrix AI and yi. So M star is something you cannot observe, but you can observe AI and this yi. And let's say you have M samples, so I is from 1 to M. So in the literature, people often write this as an operator. So you apply this big A. Okay, big A apply on M star equals to Y, which is in M dimensional vector. And in this literature, you need to have some assumption about this operator A. Such a property is called a restricted symmetry property. Basically, it assumes that for any rank K matrix M, the norm of this A applied on M, so it's M dimensional vector, is very close to the norm of the unknown or this underlying matrix M. Okay, up to some multiplicative perturbation delta. So delta usually is very small. And you can guarantee this probability if you just randomly sample this A's from a Gaussian distribution. So if you randomly sample AI's from Gaussian, then you can guarantee this RIP condition. So this is some quick background about matrix sensing. So a natural approach to recover this M star is called it's this kind of factorization approach. Okay, so we know that this M star is low rank. So instead of just representing M star as an n by n matrix, we re-parameterize it as the matrix product of two matrices, say X and X transpose. So here we consider a symmetric sensing case. So we can represent M star as XX transpose. Okay, and it's natural to use the quadratic laws. So it ended up with this loss function. So it's a sum I from 1 to n yi minus inner product between ai and xs transpose, and we try to optimize this x. Okay, and here again, in our work, we just consider the gradient descent algorithm with random initialization. So each so x is our learning parameters, and we initialize x at or at x0 from some Gaussian with some scaling parameter alpha. So this alpha square is a this Gaussian distributions variance. Okay, so this topic is about over-parameterization. So in this setting, if k equals to r, okay, so remember here we optimize over n by k matrix, and the underlying rank of this matrix m star is r. So if k equals to r, it means that our learning model has exactly the same rank as underlying model. So that's what we call exact parameterization. So in practice, oftentimes you don't know the exact rank of the underlying matrix, right? So instead, you kind of do this over-parameterization. So you allow some redundancy. So you choose some k that you are sure that it's bigger than r, and you optimize over this n by k matrix, okay, and k bigger than r's case. Okay, this is more relevant in practice because r is unknown. Okay, so again, let's look at some in simulation studies. So if you do exact parameterization, you can actually achieve global linear convergence rate. Okay, this corresponds to this green line here. So here r equals to 2, k also equal to 2, and n equal to 50. And you have this nice linear convergence approaching the numerical arrow, floating point arrow. On the other hand, if you do over-parameterization, even if a slight over-parameterization, say k equals 3, r equals 2, or k equals 5, r equals 2, then suddenly your convergence rate becomes much slower. Okay, so it corresponds to this orange and this blue lines. So again, you can take the log of the loss. You can see here the convergence rate exactly is approaching 1 over t squared. Okay, so this is exactly the same behavior we observed in the first part of talk, where in the over-parameterized case, you have an exponentially slower convergence rate compared to the exact parameterization case. And this phenomenon is for the matrix sensing the first observed in Zhang et al. In 2021. And they proposed a new method based on preconditioning to recover this exponential or this linear convergence rate in the over-parameterized case. Okay, so here let me briefly mention the prior results. In 2021, there's a paper showing random initialized gradient descent converts to some in a region which is polynomial in the initialization scaling. So it's not a global convergence rate per se, but you can find a very small error, which in terms of the initialization, if we initialize very small, then you can find a point which is polynomial in the error is polynomial in the initialization scaling. And there's an older work by Tu et al. They show the linear local convergence rate. This is all in the exact parameterization case. But basically, combining this two work can show a global convergence rate at a high level, although it needs some kind of tweaks to actually give this proof. And in the over-parameterized case, the same paper in 2021, they showed randomized gradient descent converge to a region with a polynomial in alpha. And Zhou et al. In 2021, they show a low convergence with 1 over t squared, which is exactly what we observe in the simulation study. So basically, you can combine these two to show an upper bound of 1 over t squared. But this is only about upper bound. So our main contribution here is that we can actually show a lower bound of this form. So suppose you use gradient descent with small enough constant step size. Then with high probability over random initialization, there exists some number of iterations, t0, such that after that, so now basically you're in the local region. In this local region, approaching the global minimum, you suffer from this 1 over t squared convergence rate. Okay, so you can see here the loss is always lower bounded by 1 over t squared. in this local region. So t is bigger than t0. So conceptually, this gives the same message as what we talked about in the first part of this talk, where if you are in the over-parameterized case, you do suffer exponentially slower convergence rate compared to the exact parameterization. And in our paper, we actually show this in a precise form, just 1 over t squared. Okay, so this is again a separation between exact parameterization and over-parameterization. So the key proof idea, if you dig into the math, is the following. So basically, say in the over-parameterized case, let's say this is actually your learning prompter. We kind of divide this space into two subspaces. One is this x tutum, it's an r-dimensional space. And let's say x hat is a k minus r dimensional space. So x is a n by k matrix, and underlying rank is r. So you can kind of view this x tutum as a signal space, where x tutum transpose to try to recover the underlying matrix M star. And actually, you can show that this part you can convert to a global minimum or recovers M star with a linear convergence rate. So this part is exactly corresponds to the exact parameterization case. But in the over-parameterization, you also have this redundant space, which is x hat. So the redundant space will convert to 0. But actually, this redundant space convert to 0 at a much slower rate. It's 1 over t squared. And this is actually what we prove. We prove that we identify this redundant space, and we show that redundant space convert to 0 at a much slower rate, 1 over t squared. The key recursion in this proof is that you can show that after each initialization, the gradient or the redundant space norm is always lower bounded by 1 minus the previous iteration's norm square times this norm square. So once you have a recursion of this form, you can show a 1 over t square convergence rate for this x hat to convert to 0. Okay. So that's a key recursion for the lower bound. So now what's more interesting is this asymmetric matrix sensing case. So in this case, you have underlying matrix is n1 by n2, so they are not the same for n1 and n2. And still, let's say it's of rank r. And similar to the symmetric matrix sensing case, you observe these yi's, which is the inner product between AI and this M star. And you have this operator, big A. And again, we assume this is RIP condition. So similar to the symmetric case, we factorize this M star as two matrices, F and G. So we try to use FG transpose to approximate this M star. So again, we consider two cases. One is exact parameterization, which means that this k equals to r. So f is n1 by k, g is n2 by k. And if k equals to r, it means that our model has the same rank and as an underlying model. So that's why we call it exact parameterization case. And if k is bigger than r, it is the over-parameterization case. Again, it's more practically relevant because r is unknown, so you allow some redundancy for k so that you can always recover, or at least has enough representation power to recover the underlying unknown matrix. So algorithm the same, is gradient descent with randomization, but here we use F0 and G0 to introduce a slightly different magnitude. I'll be more specific later, and this is actually a key in establishing some global convergence. So let's look at the simulation study, okay, for different initialization scaling alpha. So different from the symmetric case, you can use either over-parameterization or exact parameterization. You can achieve linear convergence rate. Okay, so on the left, it is exact parameterization. If you use different initialization scaling, they roughly have the same convergence rate here. On the right, these are the convergence rate for over-parameterization. Although if you use a larger alpha, smaller initialization, smaller alpha, your convergence rate becomes smaller. but they are still linear convergence straight. Okay, so basically from the simulation study, you can find that exact parameterization case, they're both an over-parameterization case. They both have linear convergence, and exact parameterization is kind of independent of the initialization scaling. But if you're in the over-parameterized case, then the over-parameterization depends on this alpha, which is an initialization scaling. And the smaller the alpha, the slower the rate. Okay, this is from simulation study. So there are several prior work in Mahdi's paper in 2023. They show that random gradient descent can find a region which is polynomial in alpha. So again, if alpha is small, then you can achieve small error, but it's not like really a global convergence. And Tu et al, they show that with some additional balancing regularization, F transpose F minus G transpose G, which kind of balances two factors of the same magnitude, then you can have a local convergence, which is exponential to the minus t. And Ma et al showed that local convergence can be achieved without even adding this explicit balancing regularization. So at high level, for the exact parameterization case, this problem is kind of proved if you combine Mahdi's paper and the Ma et al.'s paper. There's a global linear convergence rate. But in the over-parameterization case, it's still widely open. Mahdi, Sultan, Katabi's paper only show that you can convert to a local region, but it's not a global convergence. The global convergence in the over-parameterized, the matrix sensing case, in the asymmetric sensing, was still open prior to our work. So first of all, we give this global convergence. So we use a slightly different magnitude for f and g. So we initialize f as a kind of 3 times larger as g. So the 3 is not very important, but we do need this difference in f and g. Okay, and then you apply gradient descent. So you can show that global convergence of this global linear convergence. And in our bound, we actually show that it does depend on this linear, this initialization scaling alpha. So basically, we show that at least in the upper bound, first of all, it's a global linear convergence, and secondly, it depends on the alpha. And the smaller the alpha, the slower the convergence rate. So to emphasize the importance of the results, this is the first global convergence of gradient descent for over-parameterized asymmetric matrix sensing, and it really depends on alpha. It matches the simulation, and we actually constructed an example showing that this dependency is kind of unavoidable. And there's a key in our proof that you need some imbalance in F and G in this asymmetric matrix sensing, and that's actually the key part that drives the redundant space to 0 with this linear convergence rate. So if you're familiar with the literature, you may find this interesting because in some prior work, including mine, we emphasize the importance of the balances between F and G, so you can have a better smoothness and like that. But actually, in terms of driving the redundant space to 0, the imbalance between F and G is a key here. So if you're more interested, you can check our paper. There's some technical insight there. Okay, so this is an interesting corollary of this asymmetric sensing upper bound. So let's say you have a symmetric M star, because M star is a symmetric. So you can apply standard symmetric factorization, parameterization, parameter M star as access transpose, and then run gradient descent. But in that case, we prove that you can only achieve 1 over t square sublinear convergence rate. So actually, even if M star, the underlying matrix, you know it is symmetric, you should still use asymmetric formulation of this form. Okay, so even if M star is symmetric, you use an asymmetric formulation, F and G transpose. So in this case, in terms of convergence rate, it's much faster. It's become the linear convergence rate. So this is quite unnatural because you know M star is symmetric. You should utilize that property, but our result actually is that you should not use that property. You should still treat that as an asymmetric matrix, because that gives you much faster convergence rate from 1 over t squared to linear convergence. All right. One last thing I would like to mention is the initialization scaling. So the convergence rate depends on initialization scaling, and oftentimes initialization scaling you need to be small so that you are in this feature learning regime. And the initialization scaling is the key to drive the redundant space to 0, because this convergence rate of redundant space depends on the difference between F transpose F minus G transpose G, this kind of imbalanced matrix. Okay. And you can show that this imbalanced matrix magnitude stay the same for all iterations. This has been proved in prior work. But if it's small, then your convergence rate is quite small. So can we do better? Can we make it even faster? So actually, we design a new algorithm, which is quite simple. It's just in one step. We re-parameterize, we kind of enforce this imbalance to have a larger magnitude. So what we did that we just re-parameterize, multiply some W on F and multiply W inverse of G, such that this FG transpose remains the same. So your output actually is the same. But this magnitude of the difference between F transpose F and G transpose G becomes constant, or much larger than what it has in the initialization phase. Okay, so basically applying this algorithm just in one iteration, you basically re-imbalance, you can achieve much faster convergence rate locally. So in this iteration, we reapply this re-imbalance, and after that, it comes out has much faster rate compared to the without using this re-imbalance step. Okay, so it's a one-line change in one iteration, but give you much faster rate for this problem in the local phase. Okay, so to conclude, the main takeaway is that we found for matrix sensing and learning single neuron case, the convergent behavior of Queensland changed dramatically in the over-parameterization setting. Prior work mainly focused on the benefits of over-parameterization, but here we found that it can exponentially slow down the convergence rate, and we actually prove it from linear to sublinear. And also some interesting dependency on the initialization scaling in the matrix sensing case. The root cause is that redundant space convergent to 0, and you only have the redundant space if you're in the over-parameterized case. At a much slower rate than the signal space converted to the ground truth. The redundant space can be viewed as an angle between student neurons or redundant space in the linear algebra sense. And if you want to speed up, you can re-parameterize. For example, it can be asymmetric. It's actually much faster than symmetric matrix sensing. You can add some additional step like a re-imbalance to avoid dependency on the initialization scaling, and you can also do some precondition as in prior work to make them much faster. Okay, so that's it about my talk. I'm happy to take more questions.
Right, thanks, Simon. Let me first stop the recording.